All right, so in this video, we're going to discuss Brooks' theorem. So one thing we can note is that we had this upper bound for the chromatic number. And when you have the complete graph or an odd cycle, we see this bound holds with equality. In the case of the complete graph, we can see that because in the case of the complete graph, the chromatic number is exactly n, because every vertex needs a distinct color. And yet the maximum degree is n minus 1 because every vertex is adjacent to exactly n minus 1 vertices. On the other hand, for an odd cycle, we have seen that you must use 3 colors. And because it's a cycle, its max degree is 2. So Brooks' theorem states that these are the only examples where this equality happens. In other words, if G is connected, then the chromatic number is at most the maximum degree, or you have an odd cycle or a complete graph. So to point out updates to this theorem, there's a famous conjecture called the Borodin-Kostochka conjecture that asks about what happens when you replace delta of G with delta of G minus 1. So the conjecture says that if the maximum degree is at least 9, then you should be able to color a graph with delta of G minus 1 colors, with the only extreme cases being the examples where the chromatic number is the clique number. So we are going to prove Brooks' theorem by induction on G. There's lots of different proofs of Brooks' theorem, so we're going to use one of the more popular ones, which is also the one in the textbook, although I'll be describing it in a way that hopefully I've simplified some of the proof. So we prove the result by induction on the number of vertices of the graph. Throughout, we're going to assume our graph is always connected. And we're going to rule out certain cases first. So suppose that the maximum degree of your graph is 1. Then your graph, since it's connected, you see that it has to be an edge. And clearly that's K1. And so that's a complete graph. Now let's suppose that the max degree is 2. Well, our graph is connected, so in this case, you either have to have a path or a cycle. You can alternate the colors on a path. The path is bipartite, and so in that case, the chromatic number is 2. If it's a cycle, the chromatic number is 2 unless it's an odd cycle. And so in this case, we see Brooks' theorem is true. So for the rest of the proof, we're going to assume the max degree is at least 3. So I'm going to be doing the cases in a slightly different order in the textbook because I find it simplifies some of the later steps. So our first case now is that G is connected, but there exists a cut vertex. So let's let C be some component of G minus V. By the induction hypothesis, the chromatic number of C union V is at most the maximum degree of C union V unless C union V is an odd cycle or a clique. In that case, the chromatic number of this graph is exactly delta of that graph plus 1. But it's worth pointing out that you're looking at this component C and we've got this cut vertex V. Well, there has to be more graph that V is attached to. So in particular, this delta of C union V plus 1 is still at most the degree of V in these two cases. Because in one case, the max degree is 2 and V has degree at least 3. In the other case, the max degree of C union V is n and V has degree at least n plus 1. But the degree of V in the original graph is at most the maximum degree. And so in particular, we can conclude that the chromatic number of C union V is at most the max degree of the graph. By the induction hypothesis, and by similar argument, if we remove C from the graph, the remaining graph also has chromatic number at most the maximum degree. Notice here that I chose to include V with the component on purpose because this puts us in a situation where V appears in both sets. And the reason for doing that is because this allows us to have control over knowing who the neighbors of V are in each graph, subgraph. In particular, let F be a delta G coloring of C union V, and G be a delta G coloring of G take away C. Note if these two functions have the same value at the vertex v, then we can combine them together to get a coloring of the entire graph. However, we can't be sure that happens, so what we're going to do is we're going to change the coloring. So for a given vertex u, we're going to define it to be g of u whenever u is not in the component c. So we're just going to use our coloring g as it already is. But if u is in c, we're going to do the shifting argument. We're going to take its original color under f, and we're going to add to it g of v minus f of v. And to make sure we're working with our proper colors, we're going to compute this modulo delta of g. So if this number becomes bigger than delta of g, subtract delta of g from the answer. And likewise, if it ever ends up being negative, add delta of g to it. So here's the claim that the result is a proper coloring of g. And so what's going on is we take our coloring of g, take away c, and we leave it alone. We look at our coloring of c. It colors vertex v with the color j. And so some other vertex color k. Our algorithm takes k, it subtracts off j and adds I to it. Notice for vertex v here, j minus j plus I is just I. More importantly, if you take an edge in C, you see that both of the colors of the endpoints got shifted by the same amount, and so because they were not equal, they're still not equal. So this shifted coloring is still a proper coloring of C, and now by permuting the colors, we know that the color of vertex V is the same in both functions. And so the resulting function really is a proper coloring of G. So now we have to deal with the remaining case. Suppose G is two connected. Now we're going to first rule out the case that there's a vertex whose degree is less than the max degree. Well, remove that vertex. G is minus V is connected, so by the induction hypothesis, its chromatic number is at most the maximum degree, unless it's a complete graph or an odd cycle. But in a similar argument to what we've had before, in that case, the max degree of G minus V is at most the max degree of G minus 1. And so the chromatic number of G minus V is at most the max degree. So in particular, we can let F be a delta G coloring of G take away V. So in other words, we've colored every vertex but V, and we're coloring V last. Well, look at the colors assigned to the neighbors of V. In the worst case scenario, they all get distinct colors, and there's degree of V many neighbors, so there's at least degree many V colors that are already in use by neighbors of V. But since the degree of V is less than capital delta, the max degree, we know that this set cannot contain every color. So in particular, there exists a color that's not in this set. Let's make V that color, and now we have a proper coloring. So now we are in the case that we have a two-connected graph with the feature that every vertex has the same degree. Then the proof is going to be finished by using this lemma that we're going to prove after we finish the proof of Brooks' theorem. So the lemma states that in this situation, we can find three vertices, u, w, and v, such that u is adjacent to w, w is adjacent to v, but there's no edge going across. And moreover, if you delete these two vertices, the resulting graph is still connected. Which means this is a typo, and I just fixed it. All right, so we're going to assume this lemma for now. We're going to take these three vertices, and we're going to do the following. We're going to create a sequence of vertices, x0 through xk, with the property that the xi through xk induces a connected subgraph for all I. The last vertex is our vertex w, and our starting vertices are u and v. So the reason why we know this is possible is because if you remove u and v, you have a connected graph. And so basically you're starting at w and creating a spanning tree. And so you're just adding one vertex at a time going. And the thing that's different is that new vertices have smaller indices until we've gotten every vertex in G minus uv. And then we add u and v at the end. But since they're both adjacent to W, this is still connected for out. All right, so suppose we've made this sequence. Now we're going to color the vertices one at a time going from left to right. So we're going to assume that we're already at the stage where we've colored the first I minus 1 vertices, where I is strictly less than k, and now I want to show you how to color the ith vertex. The thing worth noting is that because this graph is connected, we know xi has to have a neighbor in I plus 1 through xk. So the neighborhood of xi must meet this in a non-trivial way. In particular, that ensures that if we look at the colors of the neighbors of xi that are earlier in the order, even if these colors were distinct, we have to have strictly less than the degree of xi many colors that have been used, because at least one neighbor occurs later. And since that's at most the max degree, this means there has to be a color available. The set of all possible colors, take away the colors that have been used on a neighbor of xi so far, must be non-empty. So then we're going to define f of xi to be the minimum element in this set. And so now we've extended the coloring, and we see that it is a proper coloring of the induced subgraph on vertices x0 through xi. All right, so this takes care of all the vertices up to the vertex xk. Now to finish off the proof, we observe that by using this algorithm, f of x0 and f of x1 both had to get the color 1. And the reason why we know this is because x1 was not adjacent to x0, so 1 was an available color when we reach vertex x1. In particular, if we look at the neighbors of xk and look at their colors, we know that we have to have strictly less than the degree of xk. Why? Because we know there's at least 2 vertices that got the same color. And so this means there must be a color available to color xk so that we have a proper coloring. So to illustrate the proof, let's actually do an example. This is known as the Peterson graph. It is 2 connected, and it is 3 regular. And here I have found 3 vertices where u is not adjacent to v, but u is adjacent to w, and w is adjacent to v. And if I delete u and v, the result is still connected. So then according to my strategy, I should label u and v as the first 2 vertices to be colored, and then label w as the last vertex to be colored, which in this case is going to get labeled 9. Its neighbor needs to be labeled 8. I see that vertex labeled 8 has 2 neighbors, so I'm going to label them 6 and 7, and then 5, 4, 3, and 2. And so now I have a labeling. And so I should be able to color this graph with 3 colors. So I'm going to color them with red, blue, and yellow, and this ordering. So that corresponds to my numbers 1, 2, and 3. So I start by coloring the first 2 vertices with red. Then I look at vertex 2. It is adjacent to a red vertex, so blue is the smallest color I can use, so I use it. Similarly, 3 is now adjacent to a red and a blue vertex. But I see there's a color available, and the smallest color available is yellow. Now if I look at vertex 4, it is adjacent to only a red vertex, so I have to color it blue. 5 is adjacent to a red and blue vertex, so I have to color it yellow. 6 is adjacent to 2 blue vertices, so I have to color it red, as that's the smallest available color. 7 is adjacent to only yellow vertices, so I have to color it red. 8 is only adjacent to red vertices, so I have to color it blue. And then finally I see 9 is adjacent to red and blue vertices. So this is the last step in the algorithm. At each case there was always a color available because there was always a vertex with a larger label uncolored that was attached to the vertex we were coloring. That's no longer true once you reach the last vertex, but because we guarantee that 2 of the vertices got the same color, we see that only 2 colors are in use, so yellow is available. However, we still have to prove this Lavash lemma, which here's the precise statement. Suppose that G is 2 connected, and K regular, so every vertex has the same degree, and K is at least 3. If G is not the complete graph, then we have to find these 3 vertices that are pairwise adjacent, but the 2 extreme ends are not. And when we delete the 2 endpoints, U and V, the result is connected. So we're going to do this proof in cases. First, suppose there's a vertex in the graph such that deleting it results in a 2 connected graph. Well, if the neighborhood of this vertex X was all the rest of the vertices, then K is the number of vertices minus 1, and the only graph that is number of vertices minus 1 regular is the complete graph. So that's a contradiction. In particular, there has to be a vertex outside the neighborhood of X. So suppose we have a path from that vertex V to X. Then I'm going to set U equal to xm minus 2, W equal to xm minus 1, and V equal to xm, also known as X. Because of this fact, I'm guaranteed that I do actually have a path of length 2 where the 2 endpoints are not together, and more importantly, since G minus X, or G minus is connected, is 2 connected, then deleting this other endpoint still gives me a connected graph. So I get exactly what I needed. So then I have to be in the remaining end case, which is that for every X, G minus X is not 2 connected. Well, I'll just take an arbitrary vertex and look at the block graph of G minus X. So by a homework assignment, this block graph is in fact a tree. And in the chapter on trees, we learned that every tree has to have at least 2 leaves. It's also not hard to show that the leaves in the block graph are actually blocks. And so we must have at least 2 leaf blocks, B1 and B2. Since they are leaf blocks, they can only contain at most 1 cut vertex from the original graph. We're going to call those cut vertices C1 and C2 respectively. Suppose that the neighborhood of X does not contain any vertex from the block other than possibly the cut vertex. Then if I delete the cut vertex from the original graph, I have separated X from the rest of the block, which means that C1 is a cut vertex for G, but that contradicts our assumption that G is 2 connected. And what we've managed to see then is that there must be a neighbor of X in each of these 2 leaf blocks. In fact, you can actually use this argument to show that there is a neighbor of X in every leaf block. But this is good enough for now. So removing one of these vertices from the leaf block does not disconnect the leaf block, and it doesn't do anything to the rest of the graph. And so we see that if we remove these 3 vertices, you end up with a connected graph. So we're almost done. We've actually managed to find a path of length 3 where the 2 endpoints are not connected. And the reason why we know they're not connected is because they're in different leaf blocks. And we know if we delete all 3 vertices, we get a connected graph. The one problem we might have left is that if we delete B1 and B2, then X is separated from the rest of the graph. However, since our graph is regular and there's this regularity parameter is at least 3, we know that X has to be adjacent to at least a 3rd vertex. And so X must be adjacent to something else in the graph. Deleting B1 and B2 does not separate X from the graph, and therefore G minus B1, B2 is connected. So that completes the proof of this lemma.